Today's lesson is going to be on advanced work and energy, especially in the way that we're going to need to understand work and energy from the IB physics standpoint. First off, we're going to talk about force and displacement graphs, and then we're going to look a little bit deeper into the work kinetic energy theorem, especially as it applies to friction, because that's going to be the most common situation. Finally, we're going to just look at a number of different scenarios and how the conservation of energy or the work kinetic energy theorem applies to those scenarios. Okay, first off, I want to look at the force displacement graph. Here we have the force displacement graph for a spring. If you remember, for a spring, the force is equal to minus kx. So here we have Hooke's law, which says the force is equal to minus kx, which if we graph it, is this sloped line right here, okay, with a negative slope corresponding to minus k, okay. And in this case, the work done to stretch the spring can be calculated as the area under the curve, okay, since work is equal to force times displacement. We're going to ignore the cosine theta because it's completely in the direction of the displacement. Okay, so if force times distance, that's what we get when we try and calculate this area under the spring. Okay, so if I calculate that, we end up with the formula listed here, which says that the work is for stretching a spring, or the energy stored in the spring, is equal to 1/2 kx squared. The reason those two terms are very synonymous is because that the force used to stretch the spring is also equal to, but opposite to, the force of the spring. Okay, and this is the energy as I stretch the spring. Where is that energy going? It's going into the elastic potential energy of the spring. So that's why the area under the curve is nothing more than 1/2 f, which is the y value, x is the x value, making the substitution and summarizing. This is how we end up with the formula for 1/2 kx squared. Now we're going to see different scenarios with force displacement graphs or acceleration displacement graphs. Okay, acceleration, anytime we see acceleration, we should understand that that's equivalent to the net force. Okay, so then we can also, those two graphs are going to be nearly synonymous, okay, with the difference of multiplying the acceleration by mass to get the force. Okay, so moving on to the work kinetic energy theorem. This theorem is important with regards to the IB. We're going to be analyzing situations using this, or this is the best approach to analyze a problem. Okay, and it says that the net work done by external forces on an object or a system is equal to the change in the object's total mechanical energy. Last year we focused only on the kinetic energy, but really it's the total mechanical energy. And recall that total mechanical energy, okay, so total mechanical energy is equal to kinetic energy plus the sum of the potential energies. Okay, it doesn't include thermal or light or some of the other odd energies, but it does include the kinetic and the potential energies. Okay, in formula form, this is the format that we will use it in, okay, that the initial energy plus any work done on the system is going to equal my final energy. Okay, and remember, we can calculate net work by summing up my individual forces and displacement, or if I know what the net force is, okay, I can use that. Okay, so for example, here I have an object of mass m. It's lifted at height h at a constant speed v. So from a kinetic energy standpoint, there's not going to be any change in my kinetic energy. Okay, what I start with is what I end with because it's a constant speed v. Okay, and in this case, I end up with additional gravitational potential energy. But where did that gravitational potential energy come from? It came from the work that was being done on the system. And in this case, I'm defining my system as both the mass m and Earth. Okay, because what I'm doing is I'm basically stretching this distance, almost like a spring. I'm stretching this distance between the object and Earth, and to do that, I have to apply a force to the object. Okay, so my work then becomes force. The force I applied was m times g, or the weight, because it stays constant speed v, so it equals the weight. The displacement, and that gives me my formula for work, or mgh, and this is also how we end up with the formula for gravitational potential energy being mgh. Okay, using it with the cosines in there, let's take another look at it. In this case, if I don't include the Earth in my system and all I have is this mass, then gravity all of a sudden becomes an external force to my system. So I have an external force, okay? And the work done at this point is going to be the work that I am moving it, my force times a force applied. The second work done is the force of gravity. Okay, in this case, the gravity is in the negative direction, so it's going to be minus, or I have the cosine 180 aspect of it. Okay, since my force is downwards and my displacement is upwards, I have that 180 degree angle in there. And the net work done is 0, which makes sense since I have no change in my kinetic energy. Okay, most of the time we'll actually be operating with the Earth in our system, but you can look at it a few different ways. Okay, friction and air resistance always point in the direction opposite the object's motion. So since it points in the direction opposite the object's motion, they'll always be taking energy away from my system, okay? And that's where the minus sign comes in. Okay, friction will remove energy from the system. For example, I have a 4 kilogram mass moving at 3 meters per second that comes to a stop after traveling 12 meters. Calculate the force of friction. Now, we could have done this using kinematics. Since I have initial velocity, final velocity, and distance, I have my 3 variables. I can calculate acceleration and multiply that by my mass to get the net force. Okay, but let's look at it from a work kinetic energy standpoint. Okay, so my initial energy, since the object was moving, is kinetic energy, 1/2 mv squared, or about 18 joules. Okay, my final energy is 0 since I come to a stop. I haven't changed height, or at least the problem doesn't say that I do. So let's assume that there is no gravitational change. And the work done, therefore, must equal the change in my energy, okay? Or 0 or about 18 joules. Since this is 18 and my final energy is 0, W then must be equal to my initial energy, or also 18 joules. Okay. So here we are. My work is 18 joules, which is also equal to the force of friction times the distance. Okay, keeping my minus signs in here, I have all my minus signs. They cancel out, however, and so I'm left with friction being 1.5 joules per meter, or 1.5 newtons. Okay? And that's the way we're going to be able to use the work kinetic energy theorem to calculate the force of friction in a different way. This way is a little bit more powerful, actually, because it applies to more situations than just the 3 kinematic variable solution. Okay, so let's look at conservation of energy in several different scenarios. As we know, energy is always conserved. It just changes forms, gravitational to kinetic primarily, but there's also friction and thermal. So let's look at it in terms of roller coasters, pendulums, and springs. Okay, first off, in the roller coaster problem, gravity will be converting gravitational potential energy to kinetic energy as my cart moves from A to B, back up to C. And at different points, we will have different values. Doesn't mean they're always going to be 0. Okay, in fact, very few of the situations will be 0. Okay, so let's look at this situation. Assume that the cart starts with an initial velocity. Okay, it has to be moving to get over that first hump. And we'll label that, we'll just call it 5 meters per second. In that case, at point A, I have gravitational potential energy based on its height. Kinetic energy based on its speed, okay? V squared, 5 squared is 25, okay? And I don't know the kinetic energies at B or C, but I will find the speeds at B and C. So at B, I have mg 10 meters, and at C, I have mg 25 meters, okay? My energy stays the same, so no matter what, GPEA plus KEA is the same as at B, is the same as at C. Okay, making the substitutions in there, I'll find that I'm going at 20.6 meters per second at B, and then 11.2 meters per second at C. So I'm going the fastest at B, a little bit slower between A and B at C. And that makes total sense as we understand how a roller coaster would work. In the case of a pendulum, this is another common situation, and we'll actually re-examine circular motion in topic 6 and simple harmonic motion in topic 9. But again, this is another situation that converts gravitational potential energy into kinetic energy, back to gravitational, back to kinetic, da 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 da. Okay, so if our objective is to calculate the speed of the pendulum bob, the bob is the mass at the end, when it passes through the equilibrium position. So here's my bob at its farthest. Okay, this is the amplitude. Okay, and it has a change in height that we label h. Okay, well, what is h? Okay, if I know the length of my pendulum, okay, my length of my pendulum being L, then this entire length is L, as is this length, L. Okay, and if I draw a right triangle in here, that means this section here must be L cosine theta. And therefore, H must be equal to L, the full length, minus L cosine theta. Okay, just a little bit of geometry. Okay, and once you have the change in height, I have mgh up here, and I have 1/2 mv squared down here. I can set those two equal, assuming it's not moving at the top, which it shouldn't be, since I said that was the amplitude point, and I can now calculate the speed of my bob given the scenario. The ballistic pendulum is something we'll also see. In this case, a block of wood captures a bullet or some projectile and moves up a certain height h. Okay, so here's my height h. Okay, and because I now know how much energy the block had at this point, I now know what its velocity at this point is, and I know energy down here because I know mgh up here. So I now know the velocity of my block initially. Okay, and given the velocity of the block and conservation momentum, which we'll talk about shortly, I can now calculate what my initial velocity of the bullet is. Okay, so I do an mgh to 1/2 mv squared, and then I do an m plus mv equals mv0, conservation of energy. Okay. Springs, okay, we can always add a spring to a problem to include a third energy type. Okay, and the energy in a spring, again, 1/2 kx squared. A couple of things to remember, that delta x represents the change from equilibrium, not the actual length of the spring, and also double check your units. Springs are often given in centimeters, but the units need to be in meters. K will have the units of newtons per meter. Okay, so for example, here I have two springs, M1 and M2, two masses, sorry, M1 and M2, and they're used to compress a spring with a spring constant of 120 newtons per meter. And I compressed this spring a distance of 8 centimeters, so there's the centimeters you need to watch out for, and then released. The question becomes, how fast are the blocks moving when the spring is released? And by conservation of momentum, the 3 kilogram block M times V will be twice the speed of the 6 kilogram block because of conservation of momentum. mv1 must equal m2v, just opposite directions. Okay, so going through the calculations, how much energy do I begin with? I have only 1/2 kx squared, okay, only the elastic potential energy, or about 0.384 joules. And at the end, I have two kinetic energies, okay? 1/2 m1v1 squared, 1/2 m2v2 squared. Using the fact that v1 must be twice v2, I can make that substitution to get a total of 9 v2 squared. Okay, and so then solving for v, and this must equal my energy of 0.384 joules. Solving for V2, I find V2 is 0.21. V1 then must be 0.41. Okay. And finally, I want to look at another way to solve my pulley problem that we looked at before. Okay. In this case, I have a mass M2 pulling a mass M1. If I look at it, then the acceleration of my system is nothing more than M2G. Okay, so my net force is M2G acting on a total force of M1 plus M2, assuming no friction. Okay, or acceleration is equal to M2 divided by M1 plus M2 times G. Okay, but we can use an energy method to solve this same problem. Okay, but to do so, let's add an extra assumption to the problem. Okay, and the assumption I'm going to make is that the block falls a distance of 1 meter. Okay, I use 1 meter because it simplifies my mgh equation. Okay, so in the beginning, the only energy I have, since block 2, falls a meter, it will have a starting energy of m2gh, or basically just m2g times 1 meter. Okay, the final energy is going to be all kinetic energy. Okay, in this case, m1 is moving, m2 is moving. They're both moving at the same speed since they're connected. If I solve for v given these equations, I find that my velocity is equal to this fairly complicated looking equation, 2m2g divided by m1 plus m2. Okay, since my initial velocity was equal to 0, my final velocity is equal to this, and the distance I traveled was equal to 1. I can now solve this using kinematics, or basically vf squared equals vi squared plus 2ad, to solve for acceleration. And I end back up with my same formula that says acceleration is equal to m2 divided by m1 plus m2g. So this is an energy approach. If you don't like the force diagrams and you get confused with the system of equations, or you can't see it as a system, this is another approach you might try to solve that kind of problem. Okay? Thank you very much.